For those of you who don't know me, my name is Justin Sachs. I'm a systems architect at ProLucid. I've been working with F# and Storm and FS Storm for quite a few months now. So I'm pretty comfortable with it, sort of still new to it, but I'm going to introduce an applied example of what Eugene was discussing called word count. Word count is sort of a quintessential demo of Storm. As far as I know, all different flavors of Storm have a word count implementation. And basically all word count is the topology produces a sentence from a list of sentences and counts the number of times it sees each word from each sentence. So my presentation is going to be pretty quick. I'm going to just go through the topology of word count. We're going to see some code of what it actually looks like, and then I'm going to actually run a couple examples of word count in action. So the word count topology is composed of three components. We have one SPOUT random sentence, which picks a sentence out of a list and emits it on its default stream. And then we have two bolts, split sentence and count words. Split sentence breaks each sentence up into individual words, and count words counts the number of times it sees each word. And so this is sort of in line with what Eugene was talking about, microservices where each component is responsible for a very small amount of work. So this is just showing how data would flow through this topology. Random sentence would pick out a sentence, emit it on its default stream, and then split sentence would emit each word individually on its default stream, going into count words, which counts the number of times it sees each word. So nothing too complicated there. Going into some code here. So this is what a SPOUT looks like, or can look like. So we have two arguments being passed into the SPOUT, runner and config. Config is a JSON configuration object that we can basically put whatever we want in. In this case, we're passing in the sentences array on the config object. Runner is implemented. FS Storm provides implementations for runner as well as emit, which gets passed into the implementation, the real implementation of the SPOUT, which you can see as an asynchronous function that actually does the work of the SPOUT. In this case, the work of the SPOUT is really just taking a sentence at random out of the sentences array and emitting it on its default stream. So the other function here is tuple. So tuple takes in an object, an array of objects, and basically it knows how to format that array in JSON form that Storm can understand. So there's a bunch of metadata that Storm puts on, that tuple puts onto that information, and then emits. Here we're passing in an ID in the form of a count, an incrementing count, into the emit function, and really that's just linking up with reliability that Storm provides us. So we're giving emit an ID that it can track acknowledgements back to. Please stop me if there's any questions.
For anyone that doesn't know F#, is there a C# equivalent to async? I mean, that's a very sort of C#, an F# idiom, right?
Yeah, so there are asynchronous tasks in C# for sure, yeah.
Just a question.
Yeah.
When I saw the tuple function, you said it took an array.
Yep.
Normally you think of a tuple as a collection of different types. So, I mean, how would I send out a tuple of multiple values of different types?
Different types?
Yeah.
So you can cast them all as objects. So it's basically an object array.
Oh.
But I don't think you need to do that,
Yeah,
right? Yeah.
The assumption is that these are objects.
Oh, okay.
Yeah.
Yeah, so it can handle any types, GUIDs, arrays. Yeah. So here we see a bolt. So the bolt takes three arguments: runner, emit, and config, all very similar to a SPOUT. The asynchronous function for a bolt takes in an argument, which is a JSON message, and obviously that JSON message is the input to the bolt. So through this message, we can access the tuple that was coming out of the previous component, as well as some metadata that I mentioned earlier, like what component the tuple is coming from and what stream the tuple was received on. So that can be handy in telling where the data is coming from. We also see anchor here. So anchor, again, it's just extending the chain of reliability down the streamline. So it's basically saying that the previous component isn't going to acknowledge until we receive an acknowledgement.
So split sentence is just a function. What makes that a bolt? But how do I know that's a bolt when I look at that?
So that's a great question and brings me into the topology.
Okay.
So this is where everything gets tied together. So as you said, split sentence is just a function, but it's actually getting passed into a bolt definition here. So the topology is where we define our spouts and bolts, as well as their configuration. So here we see how the sentences array gets passed into the random sentence spout through its configuration object. And this kind of dependency injection we can also see is happening with the runner and emit, where we're pulling out storm implementations of these functions and passing them into our components. And
So what here is F# and what here is the domain-specific language? What are we seeing? Is this the DSL here inside the topology, or is that just ordinary F#?
no, this is all F#.
Right. Okay.
Yeah. So the dependency injection that we're seeing here becomes really useful for unit testing your components, as Eugene was referring to. I think in the project I'm working on, we probably have more unit test code than actual code.
So you mean you can put in any spout or bolt in any place and you can create test topologies?
No, you're actually unit testing individual components. So so I can pass in, it's not a great example, but so word count, for example, the word count bolt here that's defined here is basically going to count the number of times it sees each word passed into it. So we're injecting a dictionary into that bolt. So you can inject anything you want. And at unit test time, we can validate that that dictionary actually has what it's supposed to have in it. As well as emit, we can invalidate that emit is populated correctly. So it's really isolating the component and making sure that it's doing what it's supposed to. And if you have good unit test coverage, then all components are working as they're supposed to, and you get very few bugs. So another thing we see here are the inputs and outputs. So spouts don't have inputs because they're the source of data. Bolts define inputs based on a certain grouping. So I think we spent a bit of time talking about this. Sometimes you don't care what data goes to which instance of a component. So in that case, we'd use shuffle, where data is just going to go wherever it goes and we don't care. However, if we're doing something like counting specific words, we want to make sure that each word goes to the same instance of the bolt so that we can get an accurate count. So in that case, we actually specify the field that we want to key off of for determining where data flows, and we'll see an example of this. So I'm going to actually run this topology now. I'll run it through normal execution, and then I'll increase the parallelism, and we can see how that input grouping comes into play. So I should also mention that I have, just for illustration purposes, my word count bolt is actually also writing to a file. So it's writing its counts to a file. Usually this should probably be done in a separate bolt. Eugene's giving me dirty looks, but just for simplicity purposes, I have that bolt calling that function. So I have Storm running in the background. I'm going to go ahead and submit my topology, which is done through an F# script. So while that's happening, I'll pull up the Storm UI. So this is provided by Storm. It's a pretty handy tool for seeing just some metrics about your topology. You can do things, reactivate, rebalance, kill the topology. You can see all your components. Oh, yeah, sorry. Is that okay? One more. One of the coolest parts of the UI is the visualization, which actually shows you how everything's hooked up. Of course, if your topology gets too big, that gets a little useless. So I can see my topology is running, and I'm getting a file. So
What are the percentages?
the percentages, I believe, are it's representing the flow of information. So 14% of my tuples are going from random sentence to split sentence. 86% is going from split sentence to word count. And that's basically because I have an average of about 6-7 words per sentence. The time is a latency, I believe. So it's the time it takes for a tuple to process and acknowledge, yeah?
The average execution time inside that folder.
Right. Yes.
Spared is end-to-end.
Exactly, because I have reliability implemented throughout the whole topology, the SPOUT is waiting for an acknowledgement from here, so it's going to take a round trip to get that. So it's about double the latency. Right, so I have my one instance of counts writing to a file with its process ID. I'm not sure if you can see that. But yeah, I have it outputting a nicely formatted list of words that it's counting, and it's still counting. So it's just going to count forever, basically. So I'm going to kill this. Now what I'm going to do is I'm going to change the parallelism of the word count bolt to 2. And I'll resubmit my topology. So you can see now there's 2 files, one for each instance of that bolt. And so if I open this up, you can see they're both running in parallel, but the key to note here is that they each have the same list of words. So the words in each component aren't changing, and that's because of the field grouping that we set in our topology. So am, apple, away, day, all these words are always going to go to this instance of the bolt, whereas these words are always going to go to this instance of the bolt. And that way they can keep an accurate count. So that's pretty much word count in action.